Let A, B, and A sub alpha, for an index alpha, be subsets of a topological space X. Prove the following. If A is a subset of B, then the closure of A is a subset of the closure of B. The closure of A union B is equal to the closure of A union the closure of B. The closure of an arbitrary union of sets contains the union of their closures. The equal is not always true. Give a counterexample where it fails. Solution. Use the definition of the closure of A. It is the intersection of all closed sets containing A. Or use this known characterization of closure. An element X of the topological space is in the closure of A if and only if, every open set that contains X intersects A. Show that if A is a subset of B, then the closure of A is a subset of the closure of B. Assume A is a subset of B. We want to show that the closure of A is a subset of the closure of B. That is, if X is in the closure of A, then X is in the closure of B. Assume X is in the closure of A. To show that X is in the closure of B, let U be any open set containing X. All we need to show is that U intersection B is non-empty. But since X is in the closure of A, we know U intersection A is non-empty. And since A is a subset of B, then necessarily U intersection B is non-empty, as wanted. Show that the closure of A union B is equal to the closure of A union the closure of B. Show both inclusions that make the sets equal. For A is subset of B, use the definition of closure. First note that A is a subset of its closure and B is a subset of its closure. Then A union B is a subset of the closure of A union, the closure of B. Now, the closure is a closed set, because the intersection of closed sets is closed. And the union of two closed sets is closed, so the union of the closures of A and B is closed and contains A union B. Therefore, the closure of A union B is a subset of the union of the closures. For the reverse inclusion, note that A is a subset of A union B. Therefore, the closure of A is a subset of the closure of A union B. Similarly, the closure of B is a subset of the closure of A union B, and therefore the union of the closures is a subset of the closure of the union. The closure of an arbitrary union contains the union of their closures. Give an example where the equal fails. The inclusion works as in B, except that now is for each A sub alpha. For each alpha prime, A sub alpha prime is a subset of the union of all A alphas. Therefore, its closure is a subset of the closure of the union, and so the union of the closures is a subset of the closure of the union. Now let's show an example where it fails. Let A sub n be the single element set with the number 1 over n natural as a subset of the reals with the standard topology. Each A sub n is closed. So on the right side, the union of the closures is the set of numbers of the form 1 over n with n natural, which are all positive. But on the left side, the union of the sets A sub n, which again gives the elements 1 over n, for every natural n, has 0 in its closure. This is because every open interval around 0 contains numbers of the form 1 over n, for some natural n, in fact infinitely many. So the closure of the union contains the number 0, and is therefore not a subset of the union of the closures, which only gives positive values.